Let's compute expected value and the variance of normal distribution with parameters a and sigma square. So here we have some random variable x with normal distribution and parameters a and sigma square. This is the PDF, which is given by 1 divided by the square root of 2 pi sigma square and times e to the minus x minus a squared divided by 2 sigma square. We need to prove that the expected value of x equals a. So it's this number right here, which is any real number which is given, right? And the variance is equal to sigma square, so to this number right here, which is a non-negative real number. So the way to compute the expected value of an absolutely continuous random variable is just computing the integral from minus infinity to plus infinity of x times the PDF, right? So we could use that right here, right now, but let me do something else before, so that it's going to be easier for us to compute the variance, okay? So look, I want to prove that some random variable y, so let me introduce some random variable y with normal distribution in parameters 0 and 1, okay? And I want to prove that x, the random variable x, has exactly the same distribution than the square root of sigma squared times y plus a, okay? So I want to prove that this random variable x with normal distribution in parameters a and sigma squared has exactly the same distribution than this random variable right here, where y has a standard normal distribution, and we multiply this by the square root of sigma squared plus a, okay? So look, we want to prove that two random variables have exactly the same distribution. For doing this, we need to prove, it's enough for us to prove that they have exactly the same CDF, right? Moreover, since x and y here are absolutely continuous, then if they have exactly the same PDF, then it means that they have exactly the same distribution. So let me prove that they have exactly the same PDF, and then this will be given, all right? So look, so let me call this like statement 1. Let me prove here statement 1. So I need to find the CDF of this, and then I need to find the derivative of that, which is going to be the PDF, and I need to prove that that PDF is going to be equal to this. So I have that the CDF of this random variable, the square root of sigma squared times y plus a in the point, let me say, u. This is given by the probability that the square root of sigma squared times y plus a is less or equal than u, okay? So the next step is to left y alone in the left side, okay? So I want only y here. So this will be equal to the probability that y is less or equal than u minus a divided by the square root of sigma squared. Okay, so and right here I have the probability that y is less or equal than this expression. So this is just the CDF of the random variable y in this point. So this is equal to the CDF of y at this point, u minus a divided by the square root of sigma squared. Okay, so in the left side I have a CDF, and right here I have a CDF. So all that I have to do right now is to find the derivative right here and right here in respective to u, and then I will get the PDF, right? So I can find the partial derivative in respective to u right here, and also the derivative in respective to u, and I will, so this will give me, this will be equal to the PDF of this random variable, square root of sigma squared times y plus a in the point u, and this will be equal to this. So the derivative of this will be the PDF of y at this point. So the PDF of y at this point, u minus a divided by the square root of sigma squared, multiplied by the derivative of the argument of this function. So multiply by the derivative of u minus a divided by the square root of sigma squared, the derivative of this in respective to u, okay? So let me now just replace the values that I have over here, and I can find the PDF. So before that, I need to find the PDF of y, but I already know the PDF of y, right? So because since y has standard normal distribution, so instead of a, I have 0, instead of sigma squared, I have 1, then I just have to replace 0 and 1 in this expression, okay? So this will be the following. So I will have that this is 1 divided by the square root of 2 pi, and e to the minus x squared divided by 2. So this divided by 2, but instead of x, I have all of this, so I will have u minus a divided by the square root of sigma squared, this squared divided by 2, okay? And I have to multiply this by the derivative of this expression, so the derivative of this is 1 divided by the square root of sigma squared, so this multiplied by 1 divided by the square root of sigma squared. And I can write this in the following way, so this will be 1 divided by the square root of 2 pi sigma squared times e to the minus u minus a squared divided by 2 times sigma squared. And this is exactly the PDF of x. So this is equal to the PDF of x in the point u. So we have proven that x and this random variable, they have exactly the same distribution. Okay, so they have exactly the same distribution. Now, why did I want to do this? Look, by the properties of the expected value, whenever I want to compute some expected value, I don't care about the random variable itself. I care about the distribution of the random variable. So these two random variables are different, but they do have the same distribution. So computing the expected value of x is exactly the same expected value of this random variable. So I will have that the expected value of x is equal to the expected value of this random variable, so the square root of sigma squared times y plus a. And now I just have to use the properties of the expected value that I know, and then I can compute this. So let me write it. So this will be, so first we need to apply linearity of expectation. So this will be equal to the square root of sigma squared times expected value of y plus the expected value of a. But a is a constant, which is given, right? So a is a real number. So the expected value of a constant is the constant itself. So this will be the square root of sigma squared times the expected value of y plus a. So all that I have to do now is to find the expected value of y. I replace the value over here, and then I will be finding the expected value of x. Okay, so the question here now is just what is the expected value of y? Okay, so I will find that in 1 second. Before that, I want to write exactly the same, but for the variance. Okay, so how can I compute the variance of x using this random variable? So look, the variance of x is equal to the variance of this random variable, so the square root of sigma squared times y plus a. So the first thing that we have to notice is that by one of the properties, if we have some random variable and we sum this random variable with some constant, right? So here we have a is a constant, then the random variable would be the same without the constant, right? So the random variable of x is equal to the variance of x is equal to the variance of x plus a. So this a doesn't change the variance, so we'll have that this is equal just to the variance of the square root of sigma squared times y. Yeah, and now we have this random variable here, and we have a constant here. So by the properties of the variance, I can take out this constant, but the square. So I will have that this is equal to sigma squared times the variance of y. So the only question now is what is the variance of y? This is what I have to find also. Okay, so I already have everything that I need to compute the expected value of x. All that I need to do now is to compute the expected value of y and the variance of y, which is easier for me because I don't have this a in sigma squared anymore. I have 0 and 1. Okay, so let's do that. So first, let's compute the expected value of y. Let me do that right here. It's going to be a very short integral, you will see. So the expected value of y is given. So all that we have to do right now is to use the formula that we know for the expected value for absolutely continuous random variable. So the integral from minus infinity to plus infinity of x multiplied by the PDF of the random variable x, of the random variable y, and the PDF is given by 1 divided by the square root of 2 pi times e to the minus x squared divided by 2 dx, right? Again, let me remind you that I obtained this from this formula right here. The difference is that a is equal to 0 and sigma squared is equal to 1. So all that I have to do is to solve this integral. Now, this integral looks quite difficult, right? But it's actually very simple. Why is that? Look, we can notice that this function, so the PDF, this function, this is an even function. So this function is even. So the graph of this function is symmetric in respective to y, yes, and so this function is even, and the function x is odd. So this is an odd function, odd function. So we have the product of an even function and an odd function. We know that this product is equal to an odd function. So the whole function here, this whole function, is an odd function. And we know that the integral from minus infinity to plus infinity of an odd function is equal to 0, right? So this is just equal to 0. So we have proven that the expected value of y is equal to 0. So this will be equal to 0. So we obtain the first result is that the expected value of x equals a. This is what we wanted to prove. So how do we compute the variance of y? So variance of y, we just have to do the formula for the variance that we know for any random variable, right? So this is the second moment of y, or the expected value of y squared, minus the expected value of y, and all of this is squared, right? Now, we already know the expected value of y because we already computed the expected value of y is equal to 0, yes? So this is 0. We already know then that this is 0. So the variance is going to be just equal to the second moment. So we'll have the expected value of y squared. Now, how do we compute the expected value of y squared? Well, this is very similar to this formula right here. The only difference is that here I had the expected value of y, of the random variable y. Here I have the expected value of the random variable y squared. So we have a function of the random variable y. This function is y squared. So instead of writing x over here, I need to write x squared. That's the only difference, right? So we have the integral from minus infinity to plus infinity of x squared. And we just write the PDF, so 1 divided by the square root of 2 pi e to the minus x squared divided by 2 dx. So we just need to compute the integral of this. So here, it doesn't help us too much to know that this function is odd and this function is, that this function is even and this function is even. We need to do something else. We need to solve this integral by parts, okay? So since we need to solve this by parts, then let me remind you what is that. So we have that whenever we have some integral that looks like this, so u dv, then this is going to be equal to uv minus v du, right? So this is called integration by parts. So this is what I want to do here, but to apply integration by parts here, all that I have to do is to find what is u and what is v, yes? So we can see that, let me write this over here. We can see the following. First, dv is going to be e to the power minus x squared divided by 2. And then I need the square of minus x squared divided by 2, so minus x. So we have minus x and dx. So this is going to be dv. Now, what is going to be u? Well, the only option left is that u have to be minus x, right? So this means that v equals e to the minus x squared divided by 2, and du is equal to sorry, I forgot here about the constant, 1 divided by the square root of 2 pi, so let me write that over here. And then du is going to be minus dx divided by the square root of 2 pi. So finally, I can replace this using this formula, and I will get the following. So this is equal to, so I will have u times v, so minus x divided by the square root of 2 pi. So this is u, v is e times e to the power minus x squared divided by 2, from minus infinity to plus infinity, okay? And then we have minus the integral of v du. Here we have v, here we have du, but here we have minus. Then since here we have minus, then this becomes plus. And then this will be equal to 1 divided by the square root of 2 pi e to the minus x squared divided by 2 dx. So look, right here, if we replace in here x by plus infinity, here I have x, so this tends to plus infinity, and here I have 1 divided by e to the x squared. This also tends to plus infinity, but this function tends to plus infinity way faster than x. That's why this tends to 0. Now, if you replace it by minus infinity, you also get that this tends to 0, right? So actually here, this is just equal to 0. Okay? And so here we have from minus infinity to plus infinity, yes? And this right here, this is exactly the PDF of normal distribution with parameters n of 1. So I have the integral from minus infinity to plus infinity of some PDF. We know that by the properties of the PDF, this is equal to 1. So this is equal to 1. So we get that the second moment, so the variance of y is going to be equal to 1. This is the variance of y. Now, all that we have to do is to replace that into the formula, this one. So we get that this is equal to 1. So the answer is sigma squared. So we get that the variance of x is equal to sigma squared.